In this video, we will look at a problem that requires very sharp observation skills. This problem recently appeared in a Codeforces round, and this is the kind of the problem where if you are not paying close attention to the details, then no matter what algorithm or data structure you have studied so far, you will not be able to solve it in an optimal time complexity. Because usually what happens is that whenever you learn a new data structure or algorithm, you try to enforce that data structure or algorithm into any new problem that you see. So you try to see, okay, can I solve it with interval DP? Can I solve it with DP on trace? But this approach can usually backfire. And if you are somebody who takes this approach, then you will not see fast growth on Codeforces. In fact, I would say that the current meta on Codeforces is highly inclined towards more observation based problems. And I kind of agree with it. Like, it should not be just bashing known algorithm or data structures that other people might not know. So this is one of these problems that kind of levels the playing field by making sure that you actually understand all the intricate details about the problem instead of just applying some patterns or tricks that you have seen before. So let's talk about the description of the problem. It says that you are given two arrays A and B. These are arrays A and B. It can contain integers, positive integers, let's say from 0 to 10 to the power 9 or any upper limit value. And you are allowed to do a series of operations on it, the order of which you can decide. And in one operation, you have to select two adjacent elements. So you pick these adjacent elements. So you pick, this is the index I and this is the index I plus 1. So since you have this array A and B, then of course they will have some values written over there, A, B, C and D. I have labeled them as such. Then you pick these four values and sort them. So once you sort them, this is the sorted order that you might get. This is just arbitrary sorted order. Then you have to delete these four elements and then add just these two elements. So in a way, if the original array contained n elements, now it will contain n minus 1 elements if you look at the individual arrays. Basically what you do is you delete A and B from here and you replace it with this second smallest element, and you delete C and D from here and you replace it with the third smallest element, which is Y. So after this reduction, of course, the array length will be reduced by 1 for both A and B. And of course, A and B will always have equal length after this reduction. So given this A, B, C, D, the idea is simple. You sort all these values and then you remove the minima and the maxima and you place this second smallest on top and the third smallest at the bottom. So now you can see that there are multiple ways to do this operation, because you can freely pick whether you want to merge these two, because essentially what you're doing is you are picking these two I and index I plus 1 and you are merging them, collapsing them together, and these four elements collapse to just two elements. So since you have multiple choices to do this collapse, then there could be multiple final results remaining. Now you can see that this set of operation, it will terminate after n minus 1 rounds. Why? Because in every round you decrease the size of each array by 1. So at the end, you know that you will have just one single element remaining, which is x over here and y over here. So you have to maximize this value. That is, what is the, you compute what is the minimum element out of these two, and whatever the minimum element comes out to be, you have to maximize that minimum. Now this is the entire problem statement, and your constraints I would mention. that it is up to 10 to the power 5 and could be as large as 10 to the power 5. So you have to come up with an optimal solution to this problem. So how do you solve this problem? So take a minute to pause this video and think about different approaches that you could try to solve this problem. So in this video, we will focus on some key observations and some thought process behind how to solve these kind of problems. Now, one thing that you can observe that you are asked to maximize the minimum element of certain quantity. And usually in these kind of problems, one thing that works usually is binary searching on the answer, which doesn't always work, but this is something that you could explore, right? So of course, binary search on answer would be a prerequisite to this video, but that is just about it. That is the only prerequisite. Interval DP or any other advanced concepts is not a prerequisite to this video. Now, let's start with the first observation. So you know that in one operation, you are taking this A, B, C, and D and you are sorting them over here and replacing it with X and Y. So one thing that you can be sure that the final answer, the final answer is in your array because you are not introducing any elements from the outside world. So this is the first observation that might not be obvious to a lot of you, that since this is just a sort operation, then your answer has to be one out of the 2n elements that are present in your array. Now let us see whether binary search would actually work on this or not. Like if we wanted to do binary search on answer, let us see if this problem even admits a binary search on answer solution or not. So suppose you wanted to know, is the answer greater than or equal to X? This is the general setting for binary search problems we have. Now, if you draw this X on the number line, suppose this is X over here, this is 1, and let's say this is infinity. Now, our goal is to maximize the final value. So, if I tell you that yes, there is a configuration in which the final answer, which is minimum of X comma Y, right, which is the minimum of X comma Y is greater than or equal to X, then since you already have a configuration in which the answer is on this side from X to infinity, would you ever want to check for the feasibility on the left hand side? The answer is no, because there is at least one configuration where the answer lies on this right hand side. So even if there are multiple configuration where the answer lies on the left hand side, why would you pick them instead of this one answer that was strictly greater than or equal to X and residing over here? Because you have to maximize the value. So uh, first check for the binary search is correct, that if the answer for greater than or equal, if this is equal to yes, this means that you don't actually have to check the left half. Why would you want to check the left half when you already have one configuration that achieves this value? So you can discard this left half. But then you also have to prove to me that if the answer is no, then you can discard the right half. So let's say if the answer for this question is no, that there is no configuration in the world where the answer is on this right half, right? So then can you actually discard this entire right half? Yes, you can do that, because suppose there is one configuration in this right half for which you shouldn't have discarded. Suppose this value was actually achievable. This value is y. But if this value is actually achievable, and if our binary search algorithm logic is correct, then why did this value not surface when I asked this query? Does there exist any answer which is greater than or equal to x? So if this told me that no, nothing greater than or x is equal to is possible, and this did not show up there, it means that this right half is actually useless, because if nothing greater than or equal to x is possible, it means that nothing on this big range is possible. So even if you try to shorten this range by looking at this smaller range, which is x plus, let's say, delta, nothing in this range will also be possible. So this means that given any x, if you can quickly find out if the answer is greater than or equal to x. I'm not talking about the case where the answer is exactly equal to x. I'm talking about the case where answer is greater than or equal to x. So you can safely discard the right half if this turns out to be false, and you can safely discard the left half. Why you can do that? Because you have already found one candidate for your answer. So why do you want to worsen the answer by looking into the left half? So one thing is clear, if we can answer this question, so let's reformulate the problem, that given x, can you find out if the answer is greater than or equal to x? Because if we can do that, then we can do a binary search on this x and we will get our answer. So let's see how do we solve this problem. Now, how do you figure out if the answer is greater than or equal to x? So once you apply this binary search, and you will remember this, that in these kind of problems, I have recently added a video on my YouTube channel, which I will also link in the YouTube description or the comments, where I talk about DP on medians, where I have told you that there is no rule book to solve DP on median. There is no rule book to solve median problems, but there is a nice trick to convert median problems to just plus ones, minus ones, and zeros. And with this conversion, we now go into a known territory where we can apply dynamic programming. So this binary search kind of follows that same principle. That is, we don't have any rule book for solving maximizing the minima or minimizing the maxima problem. But once you apply the binary search, suppose you want to apply the binary search and answer trick on this part, where you want to know if the answer is greater than or equal to x, then you can go to each element. Suppose this element is a, then you can see that if a is greater than or equal to x, you replace it with a 1. But if a is strictly less than x, you replace it with a 0. So now you see that we are already moving into a known territory, which is a binary string of consisting of zeros and ones. So suppose after this conversion, it could look like 0 1 1 1 0 0 1 1 1 1 0 1 0 0 1 0, and so on. So in this reduced version, what is the final state that we want to achieve? What final states are achievable? So final states could either be 0 0, or it could be 1 1, or it could be 0 1, or it could be 1 0. Now here, if you have been noticing closely, you will realize another sharp observation that is actually not obvious to see, is that the problem is asking you to maximize the value of this minima. But if you look at this algorithm that we are applying, that is, we are sorting, and then we want to place the smallest the second smallest over here, and the third smallest over here. This means that even though the problem tells you to minimize x comma y, if you have been noticing carefully, minimum of x comma y is actually equal to x. Why is that? Because we placed the second smallest element over here and the third smallest over here. This means that y will always be greater than or equal to x. This means that if you want to find out if the answer is greater than or equal to x, it means that you have to have a 1 at this position, and then if you are having a 1 at this position, you will want to have a 1 at this position also, because this 1 0 is not an acceptable answer, because this means that this element did not actually participate in any of the rounds. So this is actually not a feasible final state. Because looking at this, you might think that, okay, either I can achieve this state or I can achieve this state, but actually if you pay close attention, only this state is achievable, because this will always be the minimum value. But if 1 is the minimum value and your array consists of just zeros and ones, then this second value always has to be 1. So this means that you have now transformed this problem to a binary string problem, where you are given two binary strings A and B, and you have to tell me whether there is a way to achieve this final state, which is 1 comma 1. This is the modified version of the problem that we would like to solve. Now you can see that all of this we have done so that we can get into a known territory and we can apply some data structures and algorithms to simplify it further. But can we do some more simplifications on this? So then you will notice that dealing with two arrays, you don't actually know a lot of algorithms that actually deal with two arrays at the same time. So our brains are well equipped to handle one single array. We know a lot of tricks to do this, right? Some greedy algorithms, some DP algorithms, and whatnot. So can we actually do some more simplification so that maybe tracking two arrays is not really needed? So let's see if we can do that. Now you will notice that the possible merges that can happen whenever you merge two elements. So every time you have to merge a block, right? Let's say you are merging this block. So this time you will only be sorting a string containing zeros and ones. So you only want to sort four integers. So how many possibilities there could be? So there could be 2 into 2 into 2 into 2, which is 16 possibilities, right? Now you can notice that some of them are actually equivalent, because let's consider this. Let's consider any index 0 and 1, and let's suppose it is being merged with this 1 comma 0. Now you know that all the operations that you are doing is taking two boxes together and you are merging them. And how are you merging them? You are sorting this A, B, C, and D, and then replacing it with the second smallest and the third smallest. Then the one thing immediately that you can conclude, and of course this is not also obvious, this also requires some observation skills, that the ordering of the zeros and ones, they actually do not matter. What matters is, can you encode this information into just one bit? So if I told you that you have one box, like let's look at a different slide. If I told you that you have one box at index I, which looks like this, and another box that looks like this, there are only four possible ways that it could look like, right? Right. So you know that whenever you merge two boxes from left, whenever you merge two adjacent boxes, you just take the elements from here and you just sort them. So you just need to keep track of the count of zeros and ones and whatever is the ordering, because this box is actually identical to this box. Why? Because you will eventually sort these elements. So this gives us another hint, and this is the next sharp observation, that you can define a new array, let's say S, and this S of I would denote, let's say you define this S of I is equal to A of I plus B of I. This means that S of I basically tracks, so this S of I basically tracks what is the sum of these two values. And when we talk about sums in the binary worlds, sum is nothing but the frequency of 1, right? So frequency of 1. So this means this can get converted to just one single integer that encodes this entire information, because the ordering does not matter. This also gets converted to one integer, which is 1. This gets converted to 0 because there is no 1, and this gets converted to 2. So now you see that we have transformed it finally to a world that we are most familiar with. And what is that world? The transformed problem, you can see, is that this is the transformed problem. Let's pick this. So you started from here, and let's say it had 0 0, and this had 1 1, this had 0 1, and this had 1 0. Then you take this A and you take this B, and you say that okay, this is 0 0, so you add their sum 0. This is 1 1, so you add their sum as 2. This is 0 1, so you add their sum as 1, and this is 1 0, you add their sum as 1. So the transformed problem is that given just one single array, see, this time you don't actually have to deal with the hassle of two arrays. Our brains are not actually that equipped to handle multiple things at once. So we have done some simplification, and then we are saying that given a single array that contains integers between 0, 1 and 2, the final state that you want to achieve is 1 comma 1, which is in this transformed state 2. So this means that you are given an array consisting of A consists of 0, 1s and 2. Can you achieve the final state of 2 when you are allowed to merge some elements? So all we have to do is we have to figure out what happens when 0 merges with 1, 1 merges with 2, 2 merges with 0, and so on. So there will be a 3 cross 3 transition matrix for the merge, and let's look at all the transitions matrix. Now let's talk about the merge. So how do we do the merge? And before we do that, in case you are watching the video, just so that you don't lose track of what we are discussing, let me actually write down the simplified version of the problem. That is, given an array consisting of 0, 1, 2, can you collapse them together to achieve a final value of 2, right? And the collapsing rule we are going to tell you right now, like what happens when two elements collapse together. Now let's say that you have this 0. If you have 0, now what happens when 0 merges with 0? This means that when 0 merges with 0, then 0 means that first box had 0 0, and this means that the second box had 0 0. So if you sort them together, the end result that you would get would still be 0. So 0 and 0 merges to create 0. Now what about 0 and 1? So this means that the first box was 0 0, and the second box, the sum is 1. It means it is 0 and 1. So when you sort them together, you will get 0 0 0 1, and 1 will cancel out, and you would get 0 over here. And what happens when you merge 0 with 2? So when you merge 0 with 2, first box will have 0 0, and the second box must have contained 1 1, and you, when you sort them, you will get 0 0 1 1. And then you have to take the second smallest, third smallest, which is 0 plus 1. Then this means that when 0 merges with 2, it produces 1. Okay. Now what about the case when 1? What is the merging strategy for 1? So again, when 1 merges with 0, this part we have already discussed in the previous slide. When 1 merges with 0, it produces 0. So we write down 0 over here. When 1 merges with 1, we write down. Okay, so we have to talk about this case. So when 1 means you will, first box will contain 0 1, and the second box might have also contained 1 0. When you actually sort them, it will produce 0 0 1 1. And then second smallest is this, third smallest is this, and their sum is 1. So 1 merging with 1 produces 1, and 1 merging with 2. Let's talk about this. So this means first box contains 0 ones, and 2 means second box contains 1 1. And when you sort them, so you will get 0 1 1 1. So this means that second smallest is 1, third smallest is 1. So 1 merging with 2 produces 2. Now finally let's talk about the case when 2 merges with anything. So when 2 merges with 0, this part we have already discussed. Let's check. 2 merges with 0 produces 1. And 2 merges with 1 produces 2. Finally, the only thing that we have to discuss is what happens when 2 merges with 2. So the first box will contain 1 comma 1, and the second box must have contained 1 comma 1. So when you sort them, you will get 1 1 1 1, and then it will produce 2. So you have the transition matrix, that is, given this problem statement, that given an array consisting of zeros, ones and 2, you have to collapse them together, and in one operation what you have to do is, in one operation you have to select two index and merge them. And how do you merge them? You check what is the first index. If it is 0 and the second index is 2, you look from your table what to do. 0 and 2 goes to where, and 1 and 1 goes to where, etc. So you know that you can do this operations in any order, and you might get several final result, and your goal is to achieve the final result of 2. So how do you solve this problem? So you can notice that this is the classic interval DP, and in interval DP, because the order of the merges that you are doing, that will influence what is the final element that is remaining, right? So if you define something like this, you say that dp of lr, or let's say dp of ijk or ijs, means can you merge the substring ai to j, or let's say can you merge the subarray ai to j to a state s, and s mean s could be in 0 1 and 2, of course, right? Or instead of merge, let me say, can you collapse the subarray into this state? Now this is of course the classical setting for interval DP. Now how do you perform the transitions? Then you might say that okay, you have to look at the last merge, because in interval DP you usually look at the first merge or the last merge. So the last merge could Suppose that last merge is happening at this index. This means that if this is the last merge, then all of these elements have collapsed into one single block, and all of these elements have collapsed into one single block, and you want to combine those blocks to create just one single element at the end. This means that if you want to figure out, you can say that if these elements have collapsed into one block and the value of the block is, let's say, LHS, the block value, the final block value could be anything. It could be 0, 1, 2, and similarly all the elements on the right hand side, they have been collapsed to a block on RHS. Then you simply do the merge for LHS and RHS, and you can you will then get the final possible value for the entire subarray. But the time complexity would of course be O of n cube. Why? Because for each subarray, you want to find out what is the optimal point where you want to do the last merge. So the in interval DP, of course, you want to say that okay, this is the optimal point where you want to do the last merge, but you don't know where this optimal point is. So you actually try all of these optimal points, and then you check, okay, if this is your optimal last merge point, then can this array be collapsed to LHS, and can this array on the right hand side be collapsed to RHS? And if they can, then I can merge LHS and RHS together to create the final state for this entire array. And this way you can solve this problem and in O of n cube for the reduced version. And since we were doing a binary search, the entire problem can be solved in n log n. So how, let's look at the implementation. So of course, first we need the transition matrix, so that we have to know when 0 merges with 0, what element it produces. 0 merges with 1, what elements it produces, and so on. So this is just the 3 cross 3 transition matrix that we had discussed, and that I have just noted down, like when two elements merges, what happens. Then this is nothing but the same thing written down in a matrix format. And then you do a binary search. That is, you say that your in this problem the highest value is 2 into n, but this algorithm will still work if the highest value is infinity, like let's say 10 to the power 18. That should still work. And then you do a binary search, and then you say, okay, for if you have fixed the threshold as x, then all the elements that are greater than or equal to x, they will be counted as 1, and all the elements that are smaller than x, they will be counted at 0. And then you do an interval dp to see if the interval dp can give you the final state of 2. If the final state of 2 is possible, it means that there is a configuration in which you can achieve greater than or equal to x. So you strip the left half, otherwise you strip the right half. So let's look at that interval dp solution. So this interval dp, you can see that since this is a known territory, because you only have to deal with zeros and ones, and you know the merging strategy for any two elements, and any two elements, whenever they merge, they only produce 0, 1s and 2. So then you figure out, okay, what is the point on the last merge. So the last merge can be for any subarray L to R, the last merge can be at any position in between. Suppose this is the last merge point, then you have to find out, okay, what are the possible states in which the left hand side could be collapsed to. This could be 0, 1, 2, and the right hand side could also be collapsed to 0, 1, 2. And if it is possible to collapse the left hand side to 0, 1, 2 and the right hand side to this value, then you collapse them using your transition matrix, and you say that it is possible to achieve a result of 0, 1 or 2. So you can see that this solution of course works. There is no doubt at all about the proof of correctness for this solution. But the time complexity is n cube log n, and n is up to 10 to the power 5. So how do you optimize? And in fact, how much actually do you optimize? Because first you have to go to n square log n, then you have to come to n log n, and actually going from n cube log n to n square log n is also not obvious from this. So you can try multiple things. I also tried a lot of things to see if we can optimize this interval dp to n square log n. I could not come up with any approach. So that's why I had to look at it from a different perspective. And that is where this sharp observation skills that we talked about earlier, right, that would come into play. So take a minute to pause this video and think about how, given the information that we have so far, that is, this is the problem that we want to solve. Forget the original problem. This is the problem that we want to solve. That given a array containing zeros, ones, and two, and this is how zero transitions, this is how ones transition, and this is how twos transition. Can you achieve a final result of two? So try to think of an approach to do that, and maybe don't focus too much on the interval DP optimization, but look at it from a fresh perspective. So this kind of creativity is what will lead you to higher ratings on Codeforces. So think about some innovative ways to look at these transitions and come up with a different strategy that doesn't actually involve DP, because DP is actually evaluating a lot of possibilities. But what if you are smart enough and you can already determine the optimal strategy without any DP? So think about it for a while. So to do that, the only thing that we can focus on is the transition matrix, because this problem in general, I think it should only be solvable via interval DP. But if your transition matrix has something special, then maybe you could optimize it. So let's look at this transitions again. So let's say that, let's see how does zero transforms. So this zero transforms from, on the right hand side we have 0 0 1. So let me write it like so. 0 going with 0, it gives 0, it gives 0, and it gives 1. Now what about the transitions for 1? So for the transitions for 1, on the right hand side we have 0 1 2. So we write this goes to 0, this goes to 1, and this goes to 2. And finally, what about 2? So on the right hand side we have 1 2 2. So we have 1, 1 2 and 2. Now focus long and hard on this. And what is the first observation that jumps out? The first thing that you can notice, this requires a bit of observation, that look at the transition matrix for 1. 1 produces a sequence which is nicely ordered, 0 1 2. This means that 1, whenever merges with x, always produces x. This means 1 is actually useless. 1 is actually not doing anything, because sooner or so, if you consider this array and 1 is available over here, over here, over here, and over here. So no matter what merges you are doing, sooner or later you will have to merge with this one. But when you do merge with this one will just produce whatever the element that you have merged with. So in fact, you can get rid of this one completely. One is not needed. One does not participate in the merge at all. So the first observation that you can see, that one does not participate in the merge, because if it does participate, it produces the same value. So this is one big discovery that we have made, is that one is an identity element. One is an identity element. So if one is an identity element, then we don't actually have to say that, okay, one will participate right now or later. But whenever one participates, even if these elements have combined to form a new state, which could be 0 1 or 2, and these elements have combined to form a new state, whatever element that one participates with, it will always produce that element. So we can actually delete all the ones from the array and our answer will not change. This is one major discovery, that you say that this one is an identity element and therefore you only have to deal with an array consisting of zeros and twos. So now let's look at what all other observations we can make. Okay, so now that we know that the array only contains three elements, which only two elements, which is 0 and 2, let us see what the transitions look like. So if you have a 0 and it combines with a 2, we know that it produces, what does it produce? It produces 1. This is what we have seen in this transition matrix. 0 and 2 combine to produce 1. And what happens when 0 combines with 0 itself? It produces 0. Now what about the case for 2? So when 2 combines with 0, we know that it produces 1. And when 2 combines with 2, it produces 2. So now try to pause this video and make some more smart observations just by looking at this transitions. So you can notice that 0 and 0 produce a 0, 2 and 2 produce a 2. This means that zeros absorb each other. You can say that zeros absorb each other, and you can claim the same things about 2. So the 2's also absorb each other. Now what is the next sharp observation that you can make is that when you have a 0 and 2, they produce a 1, but we know that 1 is an identity element. So this means that 0 and 2, they collapse and vanish because they produce an identity element, and that doesn't change the answer because you want to produce 2 at the end. So you can say that 0 and 2 collapse and vanish. In other words, see, what is your most valuable asset? Your most valuable asset is 2 because you want to retain a 2 at the end. But if you see, if a 0 sees a 2 adjacent to it, you can say that this 0 eats your 2. 0 eats 2. So with all of this in mind, now that we know that the array can only contain a run of zeros followed by a run of twos followed by a run of zeros followed by a run of twos followed by a run of zeros and so on. And we know that if you wanted, you can actually compress this entire run down to a single zero. Why? Because zeros can absorb each other, twos can also absorb each other. Then you can compress it down to a single run, then you can compress it down to a single run, and this sequence would be something like this, right? And then you can see that since 0 and 2, they eat each other and produce 1, and then 1 vanishes, so doesn't matter. So they will cancel out, they will cancel out, they will cancel out, they will cancel out. At the end, the only thing that matters is that with this greedy strategy, will a 2 be remaining or not? So this strategy is correct, but almost like you just have to focus on just one minor thing. It's the fact that sure, zeros can absorb each other, like the entire run of zeros could become just one entry one, just 1 0. But these twos, they can also absorb each other, but you will realize that actually it might not be a good idea to absorb all the two together. For example, if you have this scenario, let's say if you have this scenario, if you have a long run of twos and you have a long run of zeros and you have a long run of twos over here, then you can see that if you if you do something like this, you collapse all the twos, you collapse all the twos over here, and then you retain two zeros, then you can see that this zero could eat this two and become one and then vanish, and then this zero could eat a two and then become one and then it will vanish. So therefore it is never a good idea to keep a long run of zeros because they can eat 1 2 on the left hand side and 1 2 on the right hand side. So it's actually better to collapse all the zeros, but for the twos it's better to it's better to do it only, it's better to just retain the terminal 2. So if you have these 2's over here, so it's better to retain this 2 and this 2. But regardless of what you do, you can see that if the number of runs, if runs of 2 is strictly greater than runs of 0, then your answer is always yes. You can always produce a final 2 at the end. So why is this greedy strategy correct? Because you can see that, so let's compress all the runs for now. Then what is the, if you have like, let's say 3 runs of 2, then it could look like 2, 2 and 2, and then you only have 2 runs of 0. So no matter where you place the runs of 0, okay, you will have to place it like so, 2 0 2 0 2. Then you can see that this 0 will eat only this 2, it will not eat this one, because you can collapse all of them into just one, and then this 0 will eat this 2, and then this 2 will be remaining. Otherwise, if you, of course, if you have more runs of 2 like this 0 and this, then this will eat this, this will eat this, this will eat this, and then this will be strictly greater, right? So all you have to check if the runs of 2 is strictly greater, because if it is equal, like if you have this 2 0 2 0 2 0 2 0, then this 0 has to eat at least one entity, so it will eat this, they will combine to create one, and then they will vanish. Then they will also eat, this will also eat, this will also eat, and then they will produce one, and the final answer would be the identity element 1. So you can see that the optimal strategy is already predetermined. You actually did not need to apply the interval DP. All you have to do is ignore all the zeros, compute the runs count of zeros and twos, which will of course be alternating. And if the run count of twos is strictly greater than 0, your answer is 1. Your answer is yes, otherwise your answer is no. So let's look at the code for that. So you iterate over this array, and if you see a 1, simply ignore it, because it is an identity element. No matter what it merges with, the answer that it produces is same. Otherwise, if you see 2's, then you start a new run of 2's, right? And you count the number of you count the runs of 2's. Otherwise you count the number, otherwise you count the runs of 1's, and then if the run of 2's is strictly greater than the run of 0's, then your answer is yes, otherwise your answer is no. So just a simple, so simple code O of n, just a greedy strategy works. No need for that complicated interval DP thing that we were doing earlier. But all of this is just in hindsight, right? This only was made possible when you made that observation, is that 1 is the identity element, then 0 eats up 2 and creates the identity element 1, which becomes useless, and then zeros and zeros absorb each other, 2 and 2 absorb each other. So these kind of the observation skills were needed to solve this problem. At least that is what I think. If you have any other easy approach that could be solved without these observations, do let me know in the comment sections. And if you have any other feedback, do let me know in the comment section. Thank you. So the final time complexity would be O of n log n, because since we are just doing the binary search, and for each binary search in O of n, we are able to compute the answer.